So in this little video we're going to take a look at the notation associated with these antiderivatives and the process of integration. So we've got the idea that these antiderivatives can calculate the area under a function. We've seen that working under a linear function. So two pieces of notation to look at. Area with no stated limits under a function. The area is given by the sum, this is a stretched S symbol, for the function xy by dx, I'm going to come to that in a moment, is given by x cubed over 3 plus c. That is the antiderivative. And this is called an indefinite integral. It's indefinite because we haven't defined any limits that we want the integral to calculate for us. So the area is the sum of x squared by dx. It's given by this antiderivative here. This is the part that does the mathematics. This is just the notation. So that's the part that's doing the work for you. And on the other side, we have the idea that we can actually calculate the area between limits under a function. And it looks like this. The area is equal to, again, our stretched S symbol to represent the total areas added up. And this time we've got a lower limit, which is called A, and an upper limit, which is called B. Applied to x squared by dx, we're going to see that in a moment. And we write that out like this. The A will be fed into the x cubed part to work out one area. The B will be fed into the x cubed later on to work out another area. And then we're going to work out the difference between the two to find a total area. So this is now a definite integral. We have defined the limits where we want to find the area underneath that function. And again, we'll keep repeating it. This is the bit that does the calculation. That is just the notation. But we want to look next at where does this dx come from. Let's move down to the box down there. Now we've already seen one example of a function and we've seen that when we take the antiderivative of that and feed in some values, we can calculate the area underneath that line there. We've seen it work. It just gives the correct answer. What we want to do now is think, can this little thing apply to other curves? And I mentioned previously the curve of, for example, the quadratic curve y equals x squared. F of x is equal to x squared. And we started to think about what it would be like to find the area under that part there. Now you should be able to see that the shapes are actually quite similar. This has got a curve in it, that's got a straight line in it. Now, how can we start to apply these antiderivatives to help us calculate that particular shape down there? Well, what we do is the same as we did when we were working out our differentiation problems. We fell back on the idea of very, very small changes in the value of x in order to make the point where we were measuring the slope as close to a straight line as we possibly could. And we can apply that idea over here. That's what this notation is doing for us. So here we have the function f of x equals x squared, and what we want to do is to imagine that we can get a value of x which is so small that the curve that's produced by the function at, say, that point there, the curve is so small that in effect it looks like a straight line. Okay, so we find ourselves a value of delta x, a very small change as we move away from one point and we go up the rest of the function. And if we make delta x small enough, then what we can actually do is build up a whole load of little rectangles, if you like, and each rectangle will have a width of delta x. So delta x means that there's a very small amount of movement along the bottom, and the actual curve of x squared, because that value is so small, is effectively just like the straight linear function that we saw there, which means that we can apply this antiderivative rule and find the area of that one, then find the area of that one, then find the area of that one, then find the area of that one, and here's where the word integration comes in. We add them all up. We find the total. We find the integral of all of these little areas added together. And the way we do that is to find some limits, a bottom limit here of a, and an upper limit here of b, and apply our antiderivative, because that antiderivative is giving us the area under a straight line. Okay? So the antiderivative is telling us that we can take the value of x cubit, divide by 3, and that would be the area for each one of these individual little pieces. Now we add to that the idea that if we make dx small enough, then in effect the height of the function up here, the position of that function above 0, is in fact the bit that we're going to integrate, and it's going to have the height of that function multiplied by dx. So we take the height of the function x squared over a very small increase in x. We multiply the two together to get an area, and sure enough, if you've got x squared and you're multiplying it by something in x, you certainly expect to get x cubed coming out of the equation. Okay? And then for each and every point, as closely packed as we can possibly get them along this line, if we add up all of those individual areas, and this is represented by this sum symbol here, the stretched s, okay, then this particular function can give us an answer. If we want an actual calculation to be made, we need to apply some kind of limit. So in this case, I could take a limit a and a limit b and ask the antiderivative to calculate all of those areas for me. Let's take a look at that working in practice, and hopefully it'll start to become clearer when we do. So what we're doing then is we're taking the function x squared, we're choosing a value of dx which is so thin that the height of the function is the one side of a rectangle, and the dx is the base of that. You multiply the two together, you get an area, and then you add up all those individual areas under a curve to get the total area. The calculation being done by the antiderivative here. So in the next video we're going to take f of x equals x squared, and we're going to find out what is the area under that curve between the values of 0 and 1.